Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on angle properties of circles. In our most recent lesson, we learned about diameters, chords, and lines of symmetry. Today, we will learn about arcs and angles. Then, we will use what we have learned to solve real-life problems. If you are ready, students, we will begin today's lesson. An arc is the distance between any 2 points on a circle's circumference. If the 2 points happen to be the circle's diameter, the arc is called a semicircle because it is half of the circle's circumference. If an arc is less than a semicircle, it is called a minor arc. If it is greater than a semicircle, it is called a major arc. In this diagram, AB is the diameter. AXB is a semicircle. AC is a minor arc, while ACBX is a major arc. Now that you are experts on arcs, let us move on to angles. There are two kinds of angles that we will be talking about today: central angles and inscribed angles. A central angle of a circle is an angle whose vertex is at the center of the circle and whose sides are radii of the circle. In this circle, you can see that angle AOB is a central angle. We say that angle AOB is subtended by the arc AXB. We may also say that angle AOB intercepts the arc AXB. An inscribed angle in a circle is an angle whose vertex is on the circle and whose sides are chords of the circle. Using the same circle as before, we can see that angle ACB is the inscribed angle. Angle ACB is subtended by the arc AXB. This brings us to the first theorem in today's lesson. The measure of a central angle subtended by an arc is twice the measure of an inscribed angle in the circle subtended by the same arc. Students, using this theorem, try to solve for x in the following 4 examples.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. In the first example, the inscribed angle is half the measure of the central angle, so we know x equals 40. In the second example, we must first determine the measure of the inscribed angle by subtracting 140 degrees from 180 degrees. Now we know that the inscribed angle is 40, so x equals 80. In the third example, remember that a straight line can still be an angle. It is 180 degrees. Therefore, x equals 90. In fact, an angle inscribed in a semicircle is always a right angle. In the final example, remember that the largest angle is actually the central angle subtended by the same arc as the inscribed angle. So, if the central angle is twice the measure, it will be 260 degrees. Therefore, x must be 100. A circle is 360 degrees. Good work, students. It was not too difficult, was it? Now that we know some of the properties of arcs and angles, we can use these rules to calculate arc lengths, perimeters, and areas of segments and sectors. Are you ready to learn the formulas, students? Good. Please get ready. The length of an arc, which we will call L, of a circle of radius that subtends a given angle is found by using this formula. Please make note of it. The formula for finding the area of a sector looks very similar, like this. As you can see, it is a ratio of the subtended angle times pi and the squared radius. This is divided by 360 degrees. There is also a formula used for measuring the perimeter of a sector. The perimeter is twice the radius plus pi times the radius and the angle divided by 180 degrees. The last formula is the biggest one. It gives us a method for finding the area and perimeter of a segment. You see that it factors in the sign of the angle as well. Good. Now it is time for an activity, students. We will give you a chance to use some of those formulas. Observe this circle. You can see that it has a segment cut out of it. The segment has a radius of 15 centimeters, but is cut off by a chord subtending a 45-degree angle at the center. Please try to find the area of the segment and the perimeter of the sector.
Students, let's get ready. Time's up. Let's get back to our lesson.
Welcome back, students. If you applied the proper formulas to the questions, it should not have been too bad. Here is the solution for the area of sector AOB. The answer is 28.125 pi centimeters squared. The area of the triangle is 1/2 times 15 squared times sine 45 degrees. That yields an answer of 225 over 2 times the square root of 2. Area of the segment is the difference of area of the sector and area of the triangle. Therefore, our answer is 28.125 pi centimeters squared minus 225 over 2 times the square root of 2 centimeters. If this was your answer, good work. Finding the perimeter of the sector may have been more of a challenge. This is what your answer should look like. It is a multiplication of twice the radius plus the length of the arc. That is all for today's lesson, students. We have learned a great deal about arcs, sectors, and chords. Next lesson, we will be studying cylinders and prisms. Until then, thank you, teacher. Thank you, students.